Hello and welcome to the fourth part of finite element mesh generation in STAAD. My name is Surajit Ghosh, and in this video I'll show you how easily we can model a concrete building structure without worrying about the beam or plate connectivity problems. In last three videos of this series, I have discussed about different mesh generation options available in STAAD Analytical Modeler and also covered how we can generate a good quality plate mesh using parametric model option. Using density line, density points and region. You should go through these videos to get a clear idea about mesh generation techniques available in STAAD. There is one problem though. We can generate a quality plate mesh using advanced mesher, but it is an one-time effort without any flexibility for future modification. In future, if we want to modify the mesh to apply a load or to add a new member within the meshed boundary, it is not possible to readjust the meshing. The only solution is to delete the entire mesh and remesh it from the scratch. What if I told you there is an option available which can generate a flexible plate mesh that can be modified anytime as per our requirement? Yes, I know this is very exciting as working with FEM is a real challenge when editing is required. Using physical modeler, we can achieve this very easily and without any extra effort. Before going into all the details about this new modeler, first I want to discuss about the necessity and background of physical objects, which is the backbone of physical modeler. I'll cover some basics. What is physical object? What are the benefits over analytical object modeling? How the data can be interchanged between these modules. Let's check the first model. This is a building structure with concrete beam and column members. I am going to isolate the top floor to investigate the member details and the connectivity. For this floor, there are several primary and secondary members present. Primary means those members connected between two columns, and secondary means those members which are connected with a primary member. When we model this, we need to ensure proper connection between all the members. Hence, we need to create intermediate nodes on primary beams to connect with the secondary beams. Due to this intermediate joint, these primary beams are divided in several parts depending on the number of intermediate connection. We call each of these individual entity as analytical objects. When we analyze a structure, each of these entities are considered for the analysis, considering proper member-to-member or member-to-plate connection. That's why we call them analytical objects.
Now, due to these internal joints, primary members divide in several parts, and this causes some problem during design phase. For an analytical model, program doesn't have any idea about the full member, and hence for concrete design, different reinforcement is provided in different span. And for steel design optimization, different section is selected for different segment of the member. This is a non-realistic condition, right? Inside, for a single member which is spanning between two columns or supports, it is not possible to provide hugely different design data. But using the analytical modeling mode, this is very tough to inform program about this full member information. Also, we cannot omit the internal nodes as they are necessary for proper member to member or member to plate connection. Else, force transfer will not be proper. Now consider a member which spans between supports disregarding the intermediate connection or joint. This full member consisting of all these segmented primary members is called a physical member. For this member, we are not considering any internal node or information about the secondary members. We are only concerned about the full member length. If the physical member data is available, then for member design, program will also provide output considering the full member length. Also, if we can model the whole structure as a physical member, then our modeling effort will be reduced as we don't have to think about the internal nodes. There comes the importance of physical modeler. Another very common example is plate modeling, whether that is a floor slab which we want to model using plate element, or a mat foundation or shear wall. In analytical modeler, we can generate a slab or wall using finite element meshing. When we model a plate mesh, all the connecting members are subdivided in smaller segments, which we called as analytical member. It is not possible to create a single plate element for entire slab, as that will not replicate a realistic condition, where the slab is connected at the corner columns only and there is no connection with the beams or interior columns. Also, as per finite element method, for a finer mesh, results will be more accurate. So we have to mesh the plate element and all the connecting members are divided, which causes both connectivity problem as well as cause problem during member design. A major problem is to consider the existing nodes during generating mesh, as if all the existing mesh present inside the panel is not considered, a connectivity problem will be occurred which we need to identify and rectify manually. This is both time consuming and sort of irritating job to identify all the connection problems and rectify them by dividing the plate elements. Physical object design is one of the solutions which can solve all these types of modeling problem. If you are familiar with older version of STAAD like the V8A series, or if you use analytical modeling mode in new STAAD.Pro Connect edition, then you are familiar with the analytical model and modeling concept. In this mode, we model from part to whole. Means, whenever we create a new member or plate, we have to ensure connection with the existing entities. Either we need to create the member using existing node, or we need to divide the members later. And the most critical one is probably the plate modeling. First, we have to ensure that the plates are properly meshed and there is a connection established with the existing beam member. If there are some plates present like existing wall, then we have to double check the connectivity between the new plates and existing plates. And if you want to modify anything like changing the geometry, then we need to delete the entire mesh and remesh again, which causes some serious connectivity issues. Now let's check the new physical modeler mode and find out how this can be helpful to model any structure. When you create a new model in STAAD.Pro Connect edition, you can find three separate modelers. Analytical modeler, which is the same old modeler of STAAD, where we can create a model based on analytical objects and need to ensure proper connectivity. Second one is the physical modeler that we will discuss today. There is another modeler called building planner mode, where we can generate a 3D model of a building structure by importing different CAD files, which includes the floor plan. We will not discuss this today. Let's focus on the physical modeler mode only. If the physical modeler mode is selected, this new interface is launched. This is a bit different from the traditional STAAD.Pro interface. Here we can generate the model from scratch up to load assignment. First, let's talk about the modeling options. If you are familiar with any CAD product, then you are probably aware that during modeling, how handy can be the UCS option. In the physical modeler, an enhanced UCS and grid option is provided. You can set your customized UCS by specifying the desired coordinate and angle value with alignment as per global coordinate, or using the 3-point method, where you can specify the coordinate of 3 nodes which forms 3-axis system. And this customized UCS can be generated as many numbers as possible. If you want to work at a particular portion of your model or want to apply some loading on your sloped roof, one of the best options is to set the UCS accordingly and then work freely with this customized UCS. For example, we can create a UCS in global axis at 000 coordinate and create a second UCS at z equals to 15 meter location. And not only that, in physical modeler, you can create a grid based on the UCS system. Just select the UCS, either global axis system or custom axis system, and other grid options like spacing or length, and that's all. Your custom grid is ready and you can use it as per your requirement. One of the most common use is when you try to create an opening in the middle of a slab or shear wall opening. Or consider applying a patch load on the slab. You can easily set your own grid as per your requirement. And finally, multiple grids can be switched on at the same time. So working on different plane is very easy now with this multiple grid. This is a concrete building structure. Same structure that I have shown earlier in analytical modeling mode. But this time, the model is created using physical modeler. I have already assigned the member property and supports. Here you can find that the beams are created as a physical member from end to end, and connection with secondary member and column is assigned internally by the program. I want to work with this model and show how physical modeler helps in modeling. First, I want to create the float slab using finite element meshing. Here, plate mesh is termed as surface. We need to select the surface cursor and select only the boundary nodes. We can change the view using right click of mouse. There is a stair hole which I want to exclude from the slab area. So bypassing this region, and the slab is created. I have not selected any internal nodes or member. Only corner nodes are selected to identify the slab geometry. Now check the analysis model generated in the background. A fine plate mesh is generated and see all the connection with the existing beams and columns. All existing nodes are considered in the mesh, and meshing is generated in line with the beams located inside the panel. There is absolutely no connectivity problem between beam and plate, as every connection is automated by the program. That's why it is very easy to generate the plate mesh as physical slab. Now if you don't like this meshing, you can simply select and delete this surface. All the members are back to its original condition. No internal nodes, no segmented member. So you can modify or delete the mesh without affecting the model. The mesh element size is optimized by the program. There is an optimization code running in the background which determines the mesh size and pattern. But you can provide the target element size to inform the program about how coarser or finer you want the meshing. From the options, you can select element type, whether triangular or quadrilateral mesh, and also the target element size. The smaller the number, the finer the mesh will be generated. It is up to the judgment of the engineer how fine the mesh should be. As the meshed surface can be altered anytime without affecting the model, so the meshing pattern or size can also be modified later. Now let me copy this surface to the bottom floors. Just select the entire surface and repeat in Y direction. We can also check the preview to find out if the surface is generated properly or not. And once we are satisfied, just click on OK. Now the slabs are generated. In same way, the stair roof slab can also be generated easily by selecting only the corner nodes. And that's all. All the float slabs are generated properly. For the shear wall, I want to create the side of the wall first. If you create the same in analytical modeler, you need to be very cautious about the existing node, beam, and also about the plate-to-plate connection with the existing slab. In physical modeler, just select the edge and the wall is created. Once again, check the analysis model. See how properly the wall slab connection is generated. Program has the intelligence to identify the existing nodes from different slab and accordingly mesh the new slab so that proper connection is established. We can freely create these meshed surfaces. Let's repeat this surface to create the opposite side wall. Just use the translational repeat command. And also create the wall in the back portion. So we need to select the corner nodes only and the wall is created. Now all the shear walls are generated. If I want to create an opening on the surface, say in the back of the wall at the ground floor, I can create a custom UCS at this location with proper coordinates and use this UCS to create a grid in the YZ plane with spacing as say 0.5 meter in both Y and Z direction. Now this grid will be used as a reference to generate the surface opening. We can create both circular and polygonal opening. For this model, I am going to generate a rectangular opening. By selecting the opening cursor, I just need to select the corner nodes and that's all. The opening is created. We can check the same in the analysis model. See how the meshing is rearranged to handle the opening portion? Let's go back to the analytical modeler. Here, all the plate meshing for slab and wall are generated. Visually, it looks great with no connectivity issues. Check the opening and the meshing around it. It is created properly. Now, it is very common that at some stage of the design, when your model is ready, your architect informs you to change something, like change the slab geometry or change the shear wall opening, probably shift the opening to left or increase the size in the vertical direction. Also, you may need to add few new floor beams. In analytical modeler, it is very hard to incorporate this change. You need to delete the entire mesh, change the geometry, and remesh the slab or wall. And as the connecting members are already divided, so new mesh might have connectivity issue with the existing beam. And until and unless you rectify these connection issues manually, this model is of no use. Let's find out how we can handle this type of change in physical modeler. Go back to the physical modeler. Say we want to change the opening. So we can simply delete the existing opening and create the new opening by selecting the new coordinates or click on the grid points. Program regenerates the mesh once again. Check the analysis model. See how the mesh is readjusted with the new opening. Go back to the analysis model. Same meshing is highlighted here with proper connection to the beam and existing slab. As physical modeler deals with the physical entity and every connection, whether that is a member to member connection, member to plate connection or plate to plate connection, all the connections are internally assigned, so it is very easy to model and modify anytime without any major effort or affecting the model. When we analyze any model in STAAD, program works with the stick model, right? So the structure geometry is formed using central line and property values are considered during stiffness matrix formation. If you look at the member alignment, you can notice that all the members are placed by their shear center. This is how STAAD places any section by default, whether that is any rectangular concrete section or steel section of different shape. Several times, due to some connection issues or other reasons, it is required to shift the section. That might be along the member length or in other two directions. For example, consider a gusset plate brace member connection where the bracing member doesn't span till the beam junction and ends in the gusset plate. So in such case, you need to assign offset value. For concrete member, it is often required to match the beam column alignment such that they are top level plus. In analytical modeler, you have to calculate the offset distance and direction manually and then assign this to the member. For thousands of members with different offset value, it is very time consuming. In physical modeler, there is an option available to adjust the alignment. See how this beam connects with the column? Now to adjust this, I can simply select the member and go to cross section position. Here several options are available how we want to place the section. If I select the top center position, then beam is placed with the top surface in same level with the column. Horizontal alignment will remain at the center of the column. This can also be modified using the top left or top right options. Let's check the rendering view. See how the member is now placed compared to the other members. Now the top surface is flushed with the column. Now let's check the analytical mode. In the specification window, you can find an offset value is assigned to this member. This offset value is calculated internally and assigned to the proper direction, so the alignment of the member is proper. It is very easy to adjust the cross section as we don't have to manually calculate the value in physical modeler, and we can simply select the member or multiple members and adjust the position. It is also required to assign rigid end joints, which means beams are connected to the column face and rest of the portion of the beam which is inside the column is considered as a highly rigid zone. Now this can also be duplicated using offset along the member length by calculating the value from column dimension. And in physical modeler, axial end offset option directly assigns the offset value to replicate the rigid end zone behavior. Now let's talk about some other features. Load assignment. In this module, we can create all types of loads like reference load cases using load group. Primary and load combination cases can also be generated. If wind and seismic definition is already created, then those loads can be added directly using the respective load definition option. We need to specify the direction of the lateral load and load factor only. This is similar to analytical modeler, so I don't want to discuss in details. Let's talk about two other load items. First one is panel loading. Consider the cantilever balcony portion. I have intentionally skipped this part from the floor slab to discuss about the panel loading. Now there are two side beams and in the front portion there is no beam. This type of hanging cantilever balcony is very common. If you want to apply any floor load on this panel, it is not possible in analytical modeler as this floor group is not closed. So either you need to calculate the load on members manually from the floor load intensity value and apply as UDL on beam, or you need to create a dummy member at the slab edge. Both is time consuming, right? In physical modeler, there is an option available called panel. This is similar to floor group but more advanced. This is just works like a reference. Using this panel option, you can generate a reference area like this, balcony area, and then use this panel for the application of load. You just need to select the edge. And once the panel is created, we can apply the panel loading. Say 3 kN per meter square load is applied in the global y direction. And we need to distribute the load. See how program distributes the load depending on the beam location. There is no load in the outer edge as there is no beam present. And all the loads distributed to the other sides. It is very easy and can handle any type of geometry, close or open, where you want to apply the floor load. There is another option available to apply load on structure, reference line. The function is similar to panel. This is not a structural element. Rather, this is just a reference along which you can add any line load. For example, an internal wall is not modeled and you want to apply the wall load directly on slab. In such case, you can use this feature. Say for this model, on the stair roof, there is an attachment along this line and I want to apply some linear load coming from the attachment. This slab is already meshed and the meshed nodes are not in line with this load. In analytical modeler, you need to create a dummy beam for this and remesh the slab once again. But here, you can simply create the reference line and use this reference line to apply the linear load in global y direction. Once again, check the meshed surface. The meshing pattern is now changed to handle the reference line load and all the meshing nodes are now in line with the load. So anytime you can add this type of loading without changing the mesh manually. Program internally handles the connection. Now let's open the complete file. This is the complete model. All supports are assigned, member properties are specified, and loads are applied. A mat foundation is created under the lift core. Check how the meshing is generated for all the slab, wall and foundation. There is absolutely no connectivity issue. Concrete property is assigned to all the members along with proper offset command. Check the load cases. First two are dead and live load cases, where I have applied the self-weight command, the gravity load, and the live load commands. Third and fourth are seismic load cases. Fifth and sixth are the wind load cases. You can see the wind intensity variation along the height is displayed graphically. Before analyzing, we can check the integrity if there is any modeling error. There are several modeling errors that can be checked from here. You can find that there are two orphan nodes present in this particular model. So we can simply use the delete option to remove it. Now transfer the model to analytical modeler. Note that in physical modeler, we can create the model up to loading. Analysis and design needs to be done in analytical modeler. Also, the model generated in physical modeler cannot be further modified in analytical modeler. You can find that the model is locked. No property or no specification value can be changed from here. The reason is analytical modeler cannot handle physical member, and if you change anything from here, that might not reflect properly in the physical modeler. If you really want to modify the model from analytical modeler, then you can detach the physical modeler file using the drop physical model option.
This model can be further used for analysis and design using advanced concrete design module. This is just an overview of physical modeler capabilities. In next video, I'll cover how we can model a box culvert very easily using physical modeler and apply different fluid, soil, and vehicle load. Stay tuned and keep watching.